Hello everyone. In the previous lecture, we learned about discrete random variables and probability distributions. Today, we want to study Bernoulli distribution. The Bernoulli distribution is considered as one of the simplest probability distribution in statistics, and it is considered to serve as a building block for more complex distributions like binomial distribution. This tutorial covers the definition of Bernoulli distribution, properties, mathematical formulations, and practical examples in Python. So first, what is Bernoulli distribution? Used to model a single trial with two possibilities. You can say success or failure, 1 or 0, true or false, right? So with two possible outcomes. It is named after the Swiss mathematician Jacob Bernoulli. Example including flipping a coin, where we had heads or tails. Or you can say passing a test, pass or fail. Or a binary, yes or no. So these are all examples of Bernoulli distribution. In here, the distribution is characterized by a single parameter p, and this p is used for success, right? And always the probability is something between 0 and 1. Then the probability of failure we show by 1 minus p. It's for failure. Again, this 1 minus p is something between 0 and 1, right? Based on this p. Whatever p is, then it is 1 minus p. The probability mass function, or PMF, for Bernoulli random variable x is p x is equal to x. If x is equal to 1, the probability is p. If x is equal to 0, then it is 1 minus p. And for the rest, for otherwise, it will be 0. For example, if you flip a fair coin, then p is equal to what? 0.5. So we can write like this: px is equal to 1 is equal to 0.5, and probability of x is equal to 0 is also 0.5. Then in here, we can go for expected value like mean. We write that ex is equal to 1 dot p plus 0 dot 1 minus p. And absolutely, because this side is 0, so ex is equal to p. The variance of x, let me clear this one. The variance, so we say that expected of x is equal to p, right? Then the variance of x or sigma square is equal to ex square minus ex square, right? So x square is equal to x, right? Because 0 square is 0 and 1 square is also 1, right? That's why ex square is equal to 1 dot p plus 0 dot 1 minus p, which is equal to p. So var x is equal to p minus p square is equal to p1 minus p. This is the variance, right? Then we can go for moment generating function, or MGF. This MGF is a tool to find moments, and it's given by mxt is equal to e of e in power of tx which is equal to p in power of t plus 1 minus p in e in power of 0, and this one is equal to p in power of t plus 1 minus p, right? So this MGF used for a random variable, and we get help to find its moments like mean and variance. The Bernoulli distribution is a special case of binomial distribution, but in here our n is equal to just 1, right? So if you repeat a Bernoulli trial n times independently, the number of sixes then follows a binomial distribution. We say x1 plus x2 plus up to xn, then follows a binomial N and P. In the next lecture, I will discuss about binomial in details. This was a very simple introduction about Bernoulli distribution. Now we want to do Python coding for Bernoulli distribution. To do that, first we will import some libraries that we need. For example, we need import NumPy as np. Then we will import Matplotlib, matplotlib.pyplot as plt. And also in SciPy, we have Bernoulli. So from SciPy.stats, we import Bernoulli. Okay. Now we set random seed for reproducibility np.random.seed. So in here we go for np.random.seed. This ensures that the random number generated by NumPy is reproducible. And this 42 is just an arbitrary number. It can be any integer. This number initializes the random generator. Then we go for parameters and we say, for example, p is equal to 0.7. Probability of success is 0.7. Then number of sample is, for example, 1000, right? Then we will generate Bernoulli random samples. Simply we say data is equal to Bernoulli. Bernoulli is from the SciPy that we have imported already. Bernoulli random variables, and we go from P, then size is equal to N, right? We generated our data. So let's see what's our data. This is our data, right? We generated 1000 data, all random. Now we want to get the mean, right? So we say mean is equal to np.mean of our data. And also variance, we get variance, and then it is np.var of our data. Then we can print it, right? So if you want to print the mean, simply we can say print, then we say if sample mean is equal to mean to f. That's all. 0.71. Then the same for variance. We can say variance here. So variance is 0.21, right? We can also go for the theoretical mean. Theoretical mean is just p, right? And theoretical variance p multiply 1 minus p, right? This one. So this is theoretical mean and theoretical variance, but what we simulation we did, it's 0.71 and 0.21. We can also plot this data. For example, we can say PLT from the Matplotlib, and we can say figure, then you can say here fixed size. Fixed size is equal to whatever you can go, for example, 5 and 5. Fixed size is 5 and 5. So this is what we generated. Then we can go for histogram, plt.histogram based on our data. Then beans is equal to 2. And edge color, you can go for example, black. And alpha as the transparency, you can say 0.8, right? Then you can determine the xtix, plt.xtix, xtix, and in here you can say 0 and 1. And then also you can say, for example, failure as 0, and success as 1, right? Then also you can determine a title for it. Title, you can say Bernoulli distribution, And here you can say, for example, P equals to P, right? And then you can say, for example, X label outcome, Y label is, for example, frequency. You can add the grid, right? Grid, true, and alpha for the transparency. You can say 0.3. So here we go. Let's make it smaller. Okay, so this is our what we did. This is based on the simulation because the probability of success was 70%, that you can see it's almost 70%. And you can see a little bit less, a little bit more because it was randomly selected, right? It does not theoretically follows, but it's simulation, it's random. Next, we can simulate different values of P and plot PMF. For example, we can say P values, like P values is equal to like 2.5 and 0.8, right? Then we can say X is equal to what? 0 and 1. Then we can say plot figure size, plot figure and fixed size is equal to 3 and 3. Then in here we say for P in P values and PMF is equal to 1 minus P and P, right? Then we can say PLT dot plot X PMF, and this is just for representation. Then we say label is equal to F dot P is equal to P, and marker size is equal to 10, right? Then we can print it. So here you can see this. Let's add some legend. So we can say plt.legend. So legend is added here. So probability of 0.2 is blue one. Probability of 0.5 is this one. It's same, right? It's uniform. Probability of this one is uniform, right? Probability of 8 is green. So you can see this one from 0 to here, 0.8, this one from 0.8 to 0.2, and this one is directly here. So here you can see the visualization of the PMF for a Bernoulli distribution. We have like here p-values 0.2, 0.5, 0.8. These define three different probability values p for Bernoulli distribution. And here we have Bernoulli random variable that can take only 0 or 1, right? Then in here, for each probability of P, we calculated PMF, right? Px is equal to 1 minus P, Px is equal to 0 is 1 minus P, and Px is equal to 1 is P. Then we plotted this using circles, as you can see here, of P and P minus 1. So plot PMF using circles and connected lines. Then the plot will this plot shows 3 PMF for 0.2, 0.5, and 0.8, be as from x is equal to 0 and x is equal to 1, right? So for p dot 0.2, px is equal to, if x is equal to 0, then probability is equal to 0.8. If x is equal to 1, the probability is 0.2. For probability of 0.5, if x is equal to 0, probability is 0.5, and if x is equal to 1, probability is 0.5. Same. Then we have probability of for p.8, If x is equal to 0, it's 0.2, as you can see here. And if it is equal to 1, it's 0.8. Each probability distribution, so in conclusion, Bernoulli distribution is foundational in probability and statistics. It is simple but powerful. It forms the basis for binary data analysis, hypothesis testing, and more advanced models. Please practice and feel free to ask me if you have any question by leaving a comment below this video. Thank you and see you in the next video lecture.